in 3.5, we're going to look at question number 1. Which one? 10. Yeah, I think we covered that one last time, didn't we? Number 10. Yeah, it should have been, let's see. It should have been B, wasn't it? If I remember right. Yep, number 10 should have been B. Yeah, I think we did that one in class last time, if I remember right. But 9 we haven't done, so we'll cover 9. So let's look at question number 1. Okay, and there's 2 types of graphic ones. There's the really simple ones, the basic ones, and then there's ones that are more complicated. So the first 1 through 3, these are the easier ones. 8, 9, and 10 are the more complicated ones. And we already did question 10 last time, I believe, in class. So you can go back and look at the notes on that one. Let's look at question number 1. So we want to graph this one. We want to graph f of x equals negative 6 over x. So the first thing we need to look at is understand what the basic graph looks like. And this is the reciprocal function, which is 1 over x. So 1 over x looks like this. F of x equals 1 over x, and this is the back cover of your textbook, so you can go back and look at it if you need to. Okay, but it looks like this. So there's your basic graph. Now, what about r's? Are we moving this up or down any? Is there a number on the end here? No. Are we shifting it left or right any? No. So, what is the basic graph going to look like? This. What does that negative 6 do? Okay. That negative 6 means we go down 6 and we go over 1. So what's our vertical and our horizontal going to be? Our vertical is the x line, and the vertical is x equals 0, and the horizontal is y equals 0. So those are our dotted lines, right? So it's going to look like this. Now, ours is going to be upside down because of the negative, though. So the vertical is x equals 0. So that's there. And the horizontal is y equals 0, which is there. Now, where do we start at? We start at where they intersect. And what are we going to be doing? Yep, and 1 over. So we go 6 down, 3, 4, 5, 6, and we go back 1. And there's our dot. Now, it needs to look like this. So remember, when we curve it, it goes towards the dotted lines, but it can't cross them. So this side looks similar to that, right? And what about the other one? We go back 1 and we go up 6. 2, 3, 4, 5, 6. And that then resembles that. There is your graph, right? So that one's a very, very simple one. All we had to do was find the vertical, and we had to find the horizontal. And the horizontal is right here at y equals 0, and the vertical is right here at x equals 0.
Wait, so what are you looking for on the
test? Okay, when I look for this, the main thing I'm going to look for is make sure these dotted lines are here, going through the origin, like that. And I'm going to make sure that it's flipped upside down from this one, right? Now, why is it flipped upside down? Because of the negative. So I want to make sure the graph looks something similar to this. It should actually curve in a little bit more, but as long as it looks similar to that, that's all that matters. So make sure you've got the dotted lines drawn in, the asymptotes, and make sure your curve is upside down because of the negative. Now the next one, question 2, is similar, but it's being slid over. So for the second one, we want to graph f of x equals 2 over x plus 3. Now, what does that 3 do? Okay, opposite of what you think it's going to do. It's a positive 3, isn't it? Right? And so you would normally think it would go positive, right? They go to the right, but you're actually going to go what? Back to the left. Okay, are we going to move it up or down any? No, nothing's on the end. Right, if there would have been like a +5, then you would move it up 5. But nothing's on the end. So where's my vertical? Yep, my vertical, not at negative 3, 0. It's just a line. My vertical line is going to be at x equals now negative 3. And the horizontal is going to be y equals 0. So what happened to my graph now? Okay, my graph has been what? Slid back to the left 3 units. So 1, 2, 3. And we make our dotted line here. And that's x equals 3, negative 3. So that's back over here. And then our horizontal is still at y equals 0. What number's on the top? So that means from where they cross, we're going to go up 2 and over 1. So up 2, right? And over 1 makes my dot right about there, doesn't it? It's above. Can it cross the dotted lines? No. So it slides like that. And what about the other side? Okay, we do the opposite. So we have to go down 2, back 1, and it looks like that. Okay. So what did we do to the graph? All we did was we basically slid it back 3 units. And instead of going up 1 over 1, we went up 2 over 1. So we made it a little bit closer in. And that's all we did. So when I'm looking for the graphs here, what my main thing that I'm going to be looking for when I grade these is to make sure I see a vertical line here at x equals negative 3, a horizontal line at y equals 0, and make sure my graph is above the dotted lines. Does that make sense on how to graph those now? Question 9 is a completely different type of problem to graph. On question number 9, we are going to be trying to use the process of elimination to graph this. So each time we do a step, we're going to go through and try to eliminate one of the choices. These take a long time to graph by hand. And I think it's more important that we can identify the different components. Instead of actually graphing it all, right, we're going to identify the different components and be able to use deductive reasoning to come up with the correct answer. So we're going to start off with the vertical. Now, from last time, when we try to find the vertical, what do? We need to set the denominator equal to what? 0. Now, this has already been factored. And that gives me x equals now what? 5 and x equals 1. Those are my verticals. Now, let's look at my choices. Okay, when I go back and I look at my choices, why is part A not going to work? Because it's got a negative 5 there, doesn't it? And what's R supposed to be? Positive 5. So we can go ahead and eliminate A. What about B? B can work, can't it? Right? Because it's got them right here. It's got 1 at 1, and one of them is at what? 5. So this one's at 1, this one's at 5. So B can still work. Now we may cross it out later on, but for right now it looks like it Could work. What about C? C is possible, right? And same thing with D, because this is at 1 and 5, 1 and 5. Okay, so now we have successfully eliminated A. What do we do after we find the vertical? Horizontal. What do? We need to divide by the largest power of x. So I'm going to go ahead and FOIL it out first. So I'm going to take care of this, rewrite it, and then divide everything by our highest power. So I'm going to go ahead and FOIL it out quickly here. So that's x squared minus 6x, right, plus 5. So now, we want to find the horizontal asymptote. And we divide everything by the highest power of x, which in this case is an x squared, isn't it? And as x goes to infinity, that goes to 0 on the top. That goes and that goes, right? And what about x squared over x squared? 1. So we now have 0 over 1, which is then what? 0. So we now know my graph has to have a horizontal line at 0. But that doesn't get rid of any of the choices, does it? Because B still has a horizontal line at y equals what? 0, so it's a possible choice. What about C and D? Same thing. Now, eventually we're going to find that C is the correct answer, but we've got to do a lot more steps to get to that point. Now, we have found the horizontal and the vertical asymptotes. What's next? Next, we find the y-intercept. And how do we find the y-intercept? We plug in 0. X equals 0. So let's go back to our original. And we're going to plug in that 0. So here's my original. Okay, here's my original right here. And I'm going to plug in 0. So f of 0 would then be 5 times 0 over 0 minus 5, 0 minus 1, and that then gives you 0 over a minus 5, right, and a minus 1, which is then 0 over 5, which is then 0. So what's my y-intercept? 0, 0. Okay, does that take care of any of the choices? No, it doesn't, does it? Well, it does get rid of B, doesn't it? Okay, why does it get rid of B? Let's look. I actually have this one labeled. Why does it get rid of B? B should have been at 0, 0, shouldn't it? But it's not actually at 0, 0. It's at what? 0, 1. So that one is gone. So now we have it down to these two. I do what now? Okay, why did we eliminate choice B? Okay, let's look at it. Let me try to draw a better. Let's see if I can zoom in a bit. And let me draw this in blue so you'll see it. Okay, so here is my curve, right? Now, it needs to go through 0, 0. 0, 0 is right there, isn't it? Okay, and look at this. This crosses up here at about 1. Right? Crosses here at about 1. So that's at 0, 1, and we need 0, 0, so we can go ahead and get rid of, then, that choice. Does that make sense now? You have to see where it crosses, and in that case, it doesn't work for us. So that one is gone. So that's why B is gone. I know it's hard to see because the graphs are so small. Now, what about C and D? Let's see if these work, C and D. Well, C works because right there is 0, 0. And D also works because it also has what? 0, 0. So we now have found that y-intercept. So let's find the x-intercept. Now you may have more than one. But let's go ahead and find our x-intercept. And how do we do that? We set f of x itself equal to 0. So that's 5x over, now let me go back to the original here. 5x over minus 5, x minus 1, and that's going to equal 0 over 1. And we end up with the same thing because we can cross multiply. And that gives you 5x equals now what? 0. Divide by your 5. And so x now equals what? 0. So that gives me the same 0, 0. So we still can't get rid of a choice there. But we do have it narrowed down to be either C or D. Is everyone okay with how I got to that point? Okay. Now, let's see if it crosses. So what do we do for the next step? We set f of x equal to the horizontal. And that's going to be where it crosses. Now, we found our horizontal to be 1. Or sorry, not 1, 0, right? We worked through this one, and we found our horizontal to be 0. And we just did that. Right? We just did this a moment ago, so we don't need to do it again. So it crosses now at 0, 0. So we just did that. We don't need to do it again. So these both cross at 0, 0. We go back and look, right? Look at this one. It crosses right there at 0, 0. This one also crosses right here at 0, 0. So we haven't got rid of either of the graphs yet. How do we figure out which one of these it is? Well, let's pick a spot and see by plotting a point where it is. Here's my 5. Okay, let's look at the difference. Now, on C, the curve is above the 0. On D, in this part on the right-hand side, the curve is what? Below 0. So we need to pick a number over here. So I'm going to pick 6. And I'm picking 6 because 6 is past this 5. So I'm going to pick 6. If it comes out to be positive, it's going to be up here, right? And it would be answer C. If it's negative, it would be down there. So let's use x equals 6. And this should give us what we need. So we need to pick another point. So we're going to pick the point or pick the value. X equals 6. And we're going to plug that in and we're going to see what we get. So plug in 6. And use your factored form. So that's 6 minus 5. And 6 minus 1, isn't it? Okay. So when I plug my values in, 5 times 6 is 30. 6 minus 5, well, that's a 1. 6 minus 1, that's a 5. So that comes out to be 6. And what's my new ordered pair? 6, 6. Okay, so which one then does it have to be? D doesn't work, right? Because D, 6, 6 is not on this curve. Right? Because this part is here and this one's here. Now, look at C. C, if I find my point and I trace it, is 6, 6. So it's right there. It's on that curve. This one is up here, right? And it's not part of that blue graph at all. So C is the correct answer, and D can be what? Eliminated. They take time to go through. That's why I'm not making you graph the entire picture. I want you to think about these and use some critical thinking, use some deductive reasoning. That's why I made them multiple choice, so you don't have to graph the entire part. I think a good skill to have is process of elimination. Because sometimes when you're given a problem, you need to think outside of the box and think of, okay, how can I approach this logically? Work through it, eliminate some of the choices, get to the only one that actually works. Sure. Right. No, because look at this one here. Okay, that one looks like it has a vertical at about 1, right? And a vertical at about 5. And it looks like 2. I know it's hard to tell, but it looks like for this one has a horizontal at y equals 0. So if we just got our vertical and our horizontal, we couldn't exclude D yet. Do you see why? And then we also can't exclude B yet either. Why? Because it looks like the vertical on B is going to be here at 1 and 5. So those work. And the horizontal is here at 0 as well, isn't it? Right? Because it goes towards it. But we could eliminate A, because A, one of the verticals is over here at -5. So that's why that one can be eliminated. Does it make sense how I did the process of elimination? Okay, did we have any others to look at out of 3, 5? And I think we did question 10 last time. I think that one should be in your notes.
Can we look at number 4?
Yep, we can look at 4 also. Okay, question 4, we want to find the vertical, if we have any. And in some cases, you may or may not have a vertical, or you may not have a horizontal, or you may have multiple verticals. You're only at most going to have one horizontal. So you either have a horizontal or not. If not, it's called an oblique, and we don't discuss obliques in this class because they're diagonals, and that's more of a calculus type of question. So we want to find the verticals for question 4. And we're going to try to find the verticals. Now, why is this one not going to have a vertical? Well, this one's not going to have a vertical because when I take my x squared plus 5 and I set that equal to 0, okay, and I move that 5 over, I get x squared equals a -5. And how do we get rid of a square? Okay, we have to take our square what? Square root. And when we take our square root, what happens with that? It's a negative underneath the root. So that comes out as I square root of 5, right? And when we go to graph things on a graph, when we look at a graph, are imaginary numbers on this plane at all? No. So this comes out to be imaginary, so that means there are no verticals. Now, if that would have been a -5 there at the very beginning, if this would have been negative, then you would have the square root of 5, and the square root of negative 5. And those would be your two verticals. But this one is positive, and when you move it over, that's what makes it not work. So that's why that one has no verticals. Does that make sense now? Okay.
And if they have like more than one, so we need one for that. Because number 5 has more than one.
Right. Number 5, okay, what would number 5 be? Okay. Because, yeah, on number 5, we have f of x equals x minus 1 over x squared minus 9, right? And so x squared minus 9 equals 0. X squared equals 9. So x equals now plus or minus 3. So that means that I have my two verticals of x equals 3 and also x equals negative 3. So that would be answer C, because you have them both. Does that make sense now? Yeah. Does that help with those now? Well, now we're going to move on, and we are now going to look at 3.7. There are a lot of sections in chapter 3 that we just don't cover, because they're not part of our outcomes and objectives. And so a lot of these sections we're not going to cover. They're very complicated and very time-consuming. We are going to look at, so we're not going to do 3.6, because that's more inequalities, and we've covered inequalities already. So I'll go ahead now and pass out the new homework packet. Does everyone have the homework packet? Yeah. Let's just turn this off on accident. Just turn this back on and we'll get started here. Let's just get the plug out. Okay. So what we're going to be looking at is 3.7, and that's variation. Now, what variation is variation is where different properties interact with each other. And this is more of physics than it is mathematics. So what we can look at is how one quantity affects another quantity. So let's take, for example, how long it takes to stop a car. Okay, what happens as I increase the speed of the car? As I increase the speed of the car, it takes longer to stop the car, right? If I'm traveling at 80, it's going to take a lot longer for me to slam on the brakes and stop than if I'm traveling at 50. That's an example of direct variation. The faster you go, the longer it takes to stop the car. One thing leads to the other. Now, there are different constants with that as well, because the type of car determines also how long it takes to stop. Some cars can stop a lot faster than others. And so on all of these, we have to find a constant. Now, that constant may be something like the effects of gravity. That constant may be something like different materials. what something's made out of, or different cars might stop at different times. But what we look at is we have to find a constant for each of these. A constant might also be something like pi when we're looking at a circle, the value of pi, 3.14. So we're going to now look at 3.7. And we're first going to learn about direct variation. And when I talk about direct variation, that means they multiply. So when we talk about direct variation, they're going to multiply. And we're going to look at three types. We're going to look at direct variation, inverse variation, which is division, and that'll be later on, and joint, where multiple things go together. Now, your direct variation formula is y equals kx. And k is a constant that we have to find. So k is going to be a constant that we must find. When we build these, I'm going to build them with words instead of using all the variables. These are pretty easy to set up. We plug our values and we find our k, and then we solve it again. So I'm on page 416. So page 416, and we're going to begin with question 28. And this is an example of direct variation. Now, the important part with direct variation means we multiply. One thing increases the other. So like think of the car. The faster the car goes, the longer it takes to stop the car. Time increases as speed increases. So let's look at 28. We're going to read it. We're going to identify it. We're going to build our equation, find our k, and then solve it again. So question 28. The pressure exerted by a certain liquid at a given point varies directly as the depth of the point beneath the surface of the liquid. Now, what does that mean? That means the further down I go, the more pressure there is, right? If I'm a diver, what happens as I go down further? Pressure increases, right? Going down more, pressure goes up. So one makes the other one go up. Now, what does it look like here? The pressure exerted by a certain liquid varies directly as the depth of that point. So the pressure is going to equal k times the depth. So pressure is what we first encounter. So our pressure equals k times the depth. And I like to use words instead of x's and y's. I think it's more confusing when you use the x's and the y's. So there's our equation. Pressure is equal to k, which is unknown, times the depth. Now they give you some starting values. So the pressure at 10 feet is 50 pounds per square inch. So the pressure is 50 pounds at a depth of 10 feet. Okay, so is everyone all right with that? So those are given. So they give you in that question, right here on 28, they give you 10 feet, 50 pounds. Now, we can find our K. So we plug our values in for the pressure, and we find our depth, and we find the K. So that means 50, that's our pressure, is going to equal the depth of 10 times the K. So divide by our 10, and that gives you now K equals So what's our new formula now look like? Our new formula now looks like, when we rewrite it, we found our K. So our formula looks like the pressure equals 5, that's our K, times the depth. Now in that case, that K was 5. But if we used a different liquid, the K might be different. Right? Maybe this is in water. Maybe you look at some other liquid. Maybe you look at mercury or something like that. Okay? It's going to have a whole different K because the way that mercury behaves and the way that water behaves with pressure are different. So K depends upon the liquid. So here's our formula. Now what do we want to do to answer this question? It says, what is the pressure at 15 feet? So the last part is we want to find the pressure at 15 feet. Well, what would we do? Okay, that 15, what does that 15 represent? That's the depth. So that tells me then that my pressure is going to equal now 5 times that 15, because that's my constant, and 5 times that 15, well, that comes out to now give you 75. So that's going to come out to be 75 psi. And that's your answer. So when we work these out, we first find our value of K, and that's going to complete our formula. Then we plug in the new values that they give you to find the next part. Now, you can use X's and Y's. I don't care, but I think if you start using the X's and the Y's, you're going to get confused as to what is what. And I like to use words. I think it's easier. I think it makes more sense that way. Let's look at another one. And let's look at 32. Okay, question 32. The amount of water emptied by a pipe varies directly as the square of the diameter of the pipe. Now, very important there, it says square of the diameter. For a certain constant water flow, a pipe emptying into a canal will allow 200 gallons of water to escape in 1 hour. The diameter is 6 inches. How much water would a 12-inch pipe empty into the canal in 1 hour, assuming the same flow rate? So let's think about what we've got here. We got a pipe like this. Okay, water's coming out of the pipe. It only lets out so much. But what happens if I make the pipe bigger? More water comes out, right? Okay. Now, how do they go together? It says they vary directly by the square of the diameter. So we need to label this so that it makes sense. So we're going to just label this as, and this is question 32. We're going to label this as just water. So that's how many gallons of water. And that's going to equal K times the diameter of that pipe squared. Because it says it varies directly as a square of the diameter. Because when you double the size of the pipe, you're not just doubling the amount of water, you're increasing it by 4 times, because 2 squared is 4. Now, what do we know? What is given here? It says, emptying in this canal, we get 200 gallons of water. So the water is going to be 200. And then that is 200 gallons in an hour, and the diameter is 6 inches. So we plug our values in. So that gives you now 200 equals K times 6 squared. So that's 36K equals the 200. Okay. And we can divide by our 36. And that gives us a K value now of, and we can just reduce this down. So it looks like, when we reduce it down, it looks like 50 over 9. So that's what your K is going to reduce down to. You can use a decimal if you want. All right, if you want to use a decimal to 2 places, you can do that as well. I just kept the fraction because this one has fractions, so I'm going to keep the fraction. So now our water is going to equal 50 over 9 times the diameter of that pipe squared. Okay, now that's our new formula. We want to change that pipe and make it, instead of a 6-inch pipe, we're going to make it a 12-inch pipe. So what's going to happen to the amount of water going through there? It's going to dramatically increase because it's going by the square. So not just doubling, because 6 to 12 would be double. It's going to increase it by about 4 times because you have to square it. So now we're going to change that diameter. And that diameter is going to be 12. So let's go ahead and plug that in. And we now have 50 over 9 times your 12 squared, which is then 50 over 9 times that 144. And 50 over 9 times 144, well, that comes out to be, when you work it out, 800. And so you're going to get out now 800 gallons of water. So a lot more, and we doubled that diameter, so we really increased the flow rate. Right, we went from 6 to 12, so we doubled the diameter and increased it by 4 times, because 200 times 4 gives you what? 800, because we doubled the diameter, right? But when you doubled it, you're actually squaring it, and 2 squared makes it 4. So that's why it went up to 800, because you had to square it. So that's direct variation. So when we talk about direct variation, we are multiplying. When we talk about inverse variation, we divide. Okay, so direct variation, we multiply. Inverse variation, we divide. And inverse variation looks like y equals k over x. And sometimes when something goes up, something else must go down. Right? With direct variation, if one goes up, the other one goes up. But in inverse, if one goes up, the other one goes down because it makes a fraction. And this happens a lot depending upon how the forces go together. So let's look at one of these where it's an inverse. 37. This one's going to be an inverse variation. Now, the only thing we need to remember is direct variation is multiply. Inverse variation is divide. That's the only difference. So question 37, we're looking at electrical current in a circuit. So electrical current flow, in electric current flow, it is found that the resistance offered by a fixed length of wire of a given material varies inversely as the square of the diameter of the wire. If we have a 0.01 diameter wire, it has a resistance of 0.4 ohms. What is the resistance of the wire of the same length and material with a diameter of 0.03 inches? And we want this to the nearest 10,000th of an ohm. Now, when we talk about resistance It's similar to what we looked at a moment ago with the flow of water. Resistance is how much more it takes to push something through. So when we talked about the water before, okay, when we increase the pipe, right, that decreased the resistance of water, so more could go through. So when we talk about electrical current, the larger diameter of the wire, the less resistance there is to the electrical current flow. It flows easier because there's more. So that's why they're inversely. So as you increase the diameter of the wire, your resistance goes down. So that's why one forces the other one to do the opposite. So let's see what we've got here. Okay, it is found that resistance offered by a fixed length of wire of the given material varies inversely to the square of the diameter. Now the key takeaway is inversely as the square of the diameter. So we now have our equation. And when we brought up our equation, what does it look like? It's an inverse variation. And what are we looking at? We're looking at resistance. And resistance is going to be K over the diameter squared. So it's just the opposite of the last one that we did. And that's why I picked 37, because it is just the opposite of the water. Right? As you increase the pipe, resistance goes down for that water and more water can flow through. Electrical current behaves the exact same way. So now what do we know? Okay, let's see. A wire of 0.01 inches in diameter has resistance of 0.4 ohms. So the diameter is, it's going to have to be squared in this case. Now, why is it squared? It doesn't always have to be squared, but it is in this case because it specifically says what? It specifically says it's inversely as the square. Now, it could be cubed or it could be square root as well, and it'll tell you those things. But in this case, it says inversely as the square, so that's why that diameter is squared. Now, the diameter of this wire is 0.01, and the resistance is 0.4. So we're going to find our K. 0.01 quantity squared. So that gives me now 0.4 equals K over, we've got to square that diameter, which is then 0.0001. And we're going to cross multiply to find our K. So we can cross multiply and we can find our K. And K looks like it's now going to be 0.1234 zeros and a 4. So there's our value of K. Now, what does K represent? Well, K represents the different types of wire. Because K is going to be different if it's a silver wire versus a copper or aluminum. Right? K is going to be different. K is based upon the type of wire. And each metal conducts electricity differently. That's why we had to find it. Because we don't know what the K is, but we can measure everything, and we can find K for that particular type of wire. Now, you can also use a table. If you're in a physics course, you look it up, a table. You should have a table with all the different types of wire, copper, silver, gold, whatever it might be. Each one of them has a different value of K. We found that, but those tables, if you took a physics course, would be in your book, and you would use this formula then to find the new resistance. So we have our K. So now we have our resistance. And that's going to equal 0.00004 over the diameter squared. That's our new formula. And we want to change that diameter. So we want to change the diameter to be 0.03. So that's going to be our new diameter. So we're going to plug in our new diameter. And we're going to see what happens to the resistance. What do you think is going to happen as I increase the diameter of this wire? As I increase the diameter of the wire, it's getting bigger, right? Resistance is going to go down because current can flow easier. So the resistance should be less because my diameter is bigger. So let's go ahead now and work it out. So I have 0.00004 over, I have to square that. So 0.03, we've got to square it. That is 0.0009. And we'll go ahead and divide those out. And then that comes out to be 0. How far does it say to round? Let's see. It says nearest 10,000. So tenths is 1, hundredths is 2, thousandths is 3, 10,000ths is 4 places. So we've got to take this out to 4 places. So that is 0.044 ohms. And you can write ohms or you can use the ohm symbol either way. Yep, that symbol represents ohms. If you take a physical science class or a physics course, you would see that is the symbol for ohms. But again, these are what you're going to see in a physics course. Why did you just 0.02? Where did this come from? Okay. That came from right here. We changed the diameter. Okay, so we went from 0.01 to 0.03. So what we always do is they give you an initial numbers. We find our K, and then we change that to something else and recalculate it again. So we find the K and then recalculate again. Okay, let's try another one. Let's look at 38, which is illumination. Okay, so 38. We're looking at the light source. Now, illumination is how many candles it looks like. So what happens as I move further away from a light source? It's less bright, right? So the further away you go, the brightness goes what? Down. That's why it's an inverse variation. Further you are away, brightness goes down. The illumination produced by a light source varies inversely as the square, inversely as the square of the distance from the source. So it's very, very similar to the last one. Inversely as the square. So what do we have? We have our illumination. Is going to equal to K over the distance squared. Okay. So there's our formula. Now we've got to plug in the values. So what do we know? It says the illumination of a light source at 5 meters is 70 candelas. So the distance is going to be 5, and the illumination is 70. And we're going to plug our values back in. So that gives you then that 70 equals K over 5 squared. So then 70 equals K over 25. And now we can just simply cross multiply, can't we? And that gives you now K is going to equal what? Well, let's multiply and see what we get. 70 times 25, that's 1750, isn't it? Okay, so there's our new value of K. Is everyone okay with how I did that? We plugged our values in, we worked it out. Now, K can change because the K value can change on that light depending upon how bright the room is, right? A brighter room, it's not going to look as bright for the illumination on the object. If it's a really dark room, it's going to look a lot brighter. So K is going to be probably determined by a variety of things. Might be how bright the room is. Now, what are we going to do after we've got our formula? Now we need to rework this formula, and we want to change it from 5 meters. We want to change it to what? 12. So the new distance is going to be 12. So we plug in our value. So we've got 1750 over 12 squared, which is 1750 over 144. And then we can go ahead and, let's go ahead and just round this out. Okay, we could break it all down. Let's just go ahead and round it out, though, and use a decimal. So 1750, we're going to divide that by 144. And it looks like it's 12 point, yep, if we round 1.5, and that's going to be candelas. So we moved further away, so what happened to the illumination factor? The illumination factor went down because we're further away, so it's not as bright. That was inverse variation. Now we're going to look at joint variation. And when we talk about joint variation, we have multiple parts or multiple variables. So when we talk about joint variation, we're going to have multiple parts working together. So lots of different things go together. Question 40 is an example of joint variation. And in joint variation, it behaves exactly the same as the others, except some might be multiplied and some might be divided. We've got multiple parts going on and affecting each other. And so we're going to be looking at it on question 40, we're going to be looking at the volume of a gas. Now, when we talk about the volume of a gas, there's several different factors that can happen and change the volume. Pressure. Okay? The amount of pressure changes the volume of the gas. Because you can compress that gas, it's going to make it go out. Also, temperature, like on a car, right? Temperature changes the tire pressure. So, what happens with the temperature? Well, if you think about a car and the tire pressure, when it's colder out, temperature goes down, tire pressure goes what? Down. Those directly vary. So let's try to come up with our formula. And this formula has to deal with the pressure and the temperature to come up with our volume. So the volume of the gas varies inversely as the pressure and directly as the temperature. Right? And we know that temperature varies directly because we can relate that back to our car tires. As temperature goes up, pressure in the car tires goes up, right? When it gets really cold out, what happens to the tire pressure in the car? It goes down. That's why you have to check your tire pressure all the time. Right? One changes the other. So let's make sure we have this set up correctly. Volume of the gas inversely as the pressure, directly as the temperature. So we're talking about joint variation because this has multiple parts. So the volume of the gas, we've got our K, our constant, and it says it varies inversely as the pressure. So pressure is inverse, so that goes below. And directly as the temperature. So there's our new equation that we're going to work with. And let's see what we've got here. Okay, so the volume of the gas is 1.3 liters. And the temperature is 300 degrees Kelvin. And if you take a physics class or a physical science course, you're going to learn about Kelvin. There's three ways that we can look at temperature. Celsius, which some of us use, Fahrenheit, which is what we use in the United States, and Kelvin. Kelvin is used more in physics because Kelvin deals with absolute zero. So we've got our volume, our temperature, and then we have the pressure, which pressure is, in this case, 18 newtons. In the United States, we use PSI, pounds per square inch. Okay, but other parts of the country might use, other parts of the world might use newtons. And that's another way of expressing pressure. So now we can fill in our pieces. So we have 1.3 equals K times the 300 over the 18. And we can work this out, cross multiply, and find our value of K. So 1.3 times the 18, that's 23.4, equals 300K, divide by your 300, and we're going to find our value of K. And the value of K, in this case, is going to be 0.078. Okay, is everyone all right with that so far? How did I get now the what? Oh, cross multiply. Because I took the 18 times 1.3, and that gave my 23.4. Rewrite our formula. And so the volume equals 0.078 times the temperature over the pressure. Okay, what are we looking at now? We want to find find the volume at 340 degrees Kelvin, pressure of 24 newtons. So the temperature now is 340, and the pressure is that 24 newtons. And that was given in the question, right? So they give you a new temperature and a new pressure. And what's our volume going to be? Well, we just plug our values in. And that's going to be 0.078 times the 340 degrees in Kelvin. Divide by that 24 for the pressure. And what's our new volume going to now be?
1.105.
Okay, times 340. Divide that by 24. And yep, that comes out to be 1.105, and that is in terms of liters. Is everyone all right with that? And that K can change. That K is going to change based upon different gases. That K would be different for hydrogen gas versus a helium gas. Right? K would be different in how they behave with pressure and temperature. So K is relating to each different type of gas. Now, also when you take a physics course or a physical science class, you're going to have different units. And we have the standard system, which is liters, kilometers, meters, things like that. And then we have the English system. So you have to convert back and forth. So that's a lot of it too, is there's two different systems. So we have to make sure that we know the difference between, let's say, a Newton and PSI, pound per square inch. They're different, but they still relate to pressure. Same thing with temperature. Let's look at one more, and this will be the last question here. Let's look at question 46. Well, let's do 47. We'll do the BMI one. So let's do 47 instead. They're both the same, but let's talk about the body mass index. Many of you are kind of familiar already with the body mass index, the BMI. Now, what happens with the BMI? There's two parts to it. The person's weight, right, and the height of that person. So, what happens when your weight goes up? Your BMI goes up, right? What happens if you look at a taller person with the same weight? If a person's taller, the BMI is what? Less. Okay, so the BMI is directly proportional to his or her weight and inversely proportional to the square of the height. Has to be in inches, though. So here's our formula for the BMI. The BMI is going to be K times the weight over the height squared. Square of the height. Now, K can be in a different number for different people. Different age groups might have a different K. Different genders have a different K. The BMI, the K value they use for women, is different than the one for men. And you can also probably change that K to be different age groups, could be a different K value, how they're calculated with the BMI. Again, BMI is just a number, and it just basically tells you, okay, how healthy are you? It's basically what it is. Are you overweight, underweight? That's what a BMI is. So what do we have? We've got a person that comes in, and a 6 foot tall person weighs 177 pounds, BMI of 24. So the BMI of this person is 24. The weight is 177. And the height. Now the height has to be in inches. So that height right now is 6 feet. So we need to make that in terms of inches. So there's 12 inches in a foot. Right, so multiply those together, and we get our 72 inches. Plug in our values. So our weight is 177K over 72 squared. And now we'll work this out. So now we've got 24 equals 177K over 72 squared. It's going to be a fairly large number. 72 squared is 5184. And then we'll cross multiply here. we get now 177K equals, looks like this, 1244.16. We'll divide by our 177, and we've got our value of K. And again, K might be different for a different gender. Men have a different K than women. So 1244.16, divide that by 177. And then that comes out to be, we'll take it out 2 places, should be enough. 702 point, looks like 92 if you round, right? Close enough. Rewrite our formula. So the BMI is now going to be 702.92 times the weight over the height squared. And we want to now change this. Okay, so we want to change this, and we want to come up with our new BMI. And a new person comes in, and that new person weighs 130 pounds, and height is 66. So let's plug in our values here. And see what our BMI comes out to be. And it says we're going to go ahead and round this out now to the nearest whole number. So we're just going to get this out to the nearest whole number. And it looks like that's going to come out to be about a BMI of 21. So that's going to be it for today. Now I have lots of things to pass out. We've got lots of things to pass out before you leave. Get things sorted out here. Many of you are leaving for the class early. So some of you might not be coming back after fall break. Because maybe you need to leave. I know I signed a lot of forms for students that need to leave early. So I went ahead and gave you your practice final. So you go ahead and start working on it now. It's not going to be due until you take the final exam. Some of you may be leaving early, so you'll have to take your final exam early. But at least this way, you've got it already and you can start working on it. If you're not leaving early, if you're coming back after fall break, we're going to cover all the material. If you're leaving early, you're going to have to learn some of that material on your own. There's not that much. But this way, you already have something to start working. So this way, if you're leaving early, and I know I've signed lots of forms, you can start working on things now. And I have an answer key to go with it as well. Pass the answer key out now. And this is how I worked out your practice problem. So this will help you understand the parts that you're missing. And the sheet for that, the first thing. And I'll talk about this in just a second to get these passed out. Okay, so let me just take a moment now to talk about that final. Okay, so we have not covered everything on that final yet. Many of you are leaving, and I've signed lots of forms. I know a lot of you are leaving because you have to go home, and it's a lot cheaper to get flights home earlier. So some of you may not come back after the fall break. If you're not going to come back after the fall break, you need to go ahead and start working on that practice final now. Then you're going to have to find some time for me and you to work together to take your final exam. Now, on your final, in that packet, there's a practice final, which I've got the key, and I gave you that as well. Behind that practice final is a take-home final, and that's designed to get you ready for that final exam. I'm giving it to you way, way early. That way, if you're not coming back after that fall break, you can start working on it now, because it's not very far away. If you're coming back, that's fine. We're going to cover everything in class. We'll cover the logarithms and all the other material. I do have the sign-in sheet, so I'll pass that out. And then I will see everyone then on Thursday. Okay, but I just gave you that.